Okay, so hello everyone. So today we are welcoming Perraut, an astronomer from IPAG, who did their PhD in Marseille about interferometry for astronomy and got the silver medal from the CNRS after. She has been involved almost since the beginning in the gravity instrument at the VLTI. And today she will talk us about the observations done with this instrument, the gravity instrument, the observations of protoplanetary disk. So Karine, the floor is yours.
Thank you, François, and thank you for the invitation. So good morning, everybody. I am very pleased to be here and to be back in Marseille for a very long. I was there a very long time ago when the institute called LAS, and I have found a very old document showing that at that time the institute was involved in optical interferometry, and not only me, but some people in the room here. And so no, I am very pleased to be here to present you the recent results we obtained with the near-infrared interferometric instrument GRAVITY installed at the VLTI in Perraut on protoplanetary disks. And just a few words of context. With more than 5,000 exoplanets detected so far, it's clear that the planet formation process is very robust and efficient. And the current population of non-exoplanets exhibit a very incredible diversity in terms of nature, in terms of mass, in terms of radius of the planet themselves, but also in terms of architecture of the system. And what is interesting when we have a look to the demographic of the detected exoplanet, for instance, when we plot the mass as a function of the semi-major axis, we can see a few interesting findings. It's first, the main outcome of this process is what we call the super Earth of mini-Neptune planets that are here, and none of which exist in our solar system. And we also see that most of the planets detected so far are within 1 AU of their central star. And there is a lot of open questions in this domain, and most of you know them probably better than me. But the questions that are about the origin of this diversity and which processes determine the final outcome of the planetary system. And if we focus on what we call the Kepler population that has been detected by the Kepler mission, and we plot, it's almost the same kind of plot, but it's on a different way. Each symbol corresponds to a system that is set in a logarithmic scale with respect to the central star. And it's just to show you that most of them are within the Earth orbit and even within the Mercury orbit, so very close to the O star. And also to set the scales. I have superimposed a scheme that is well accepted now in the young solar system description, that is the magnetospheric accretion scenarios. And for the young sun, the T-Tauri stars, we think that the inner disk is truncated by the magnetic field of the star and force the material to accrete onto the star, following the magnetic field line that is in red here. And this is the scales of this process. It's around 0.005 or 0.a few. And so what we would like to do is really to probe this case to understand which initial conditions have to be in place to favor these low mass close-in planets. So of course, to understand that, we need to explore the birthplace of the exoplanet, that is to say the protoplanetary disks, and because these disks are the reservoirs of material from which matter is accreted onto the star and from which planets are built. And these disks are mostly constituted of gas with a small fraction of the grains. And what is really important to understand is that the star formation, the planet formation, and the evolution of the disk and of the star influence each other, because the radiation of the central star will irradiate the disk, the inner part of the disk, but also the nascent protoplanet, and the accretion and the ejection of material will also set finally the conditions for the star and the planet evolution. And even if these interactions are brief and can last a few million years, they are foundational because they set the initial conditions for planet formation, and they set also the properties that persist for billions of years. So if we would like to understand the outcome of planet formation, we really need to look at the structures and the evolution of the protoplanetary disk while the planet formation is happening. So you probably know this beautiful gallery of images, because looking at the protoplanetary disk has been done for several years now, either in a near-infrared scattered light with SPHERE, or in the millimetric range with ALMA, for instance. And you see that whatever the spectral type here, we can see these beautiful features. We can see rings, we can see gaps, spirals, and shadows, and all of them can be a signpost of planets. And here I give you also an idea of the scales, and we see also that the scales and the features can be very different. But in that case, we are probing what we call large scales, so a few tenths of AU, and so we see that when looking at the dust, it's very dynamic. But when looking at the gas, for instance, in the CO map here obtained with ALMA, we also see some features and kinematic pattern showing that all these environments are very dynamic. And what we would like to do to have a global view of this protoplanetary disk is really to zoom in and to have a look to what happened behind the gray zone is the coronagraph of SPHERE. So it's really to zoom in and to have access to these regions that we call the star disk interaction regions. So this is the scheme you have here, and you have an idea of the scales. And so this is the region when the dust of the disk is sublimated due to the irradiation from the central star. The dust grains can settle, can be trapped in different zones in the disk, and they can also be grown to pebbles that are the building blocks of planets. But material can be also ejected through disk, either at the disk level, through wind, sorry, either at the disk level or at the star level. And the material can be also ejected through jets. So this is the region where accretion and ejection processes occur, and of course impact the evolution of the disk and the planet formation process. So to do that, we will use optical long baseline interferometry, because if we go back to the scale, so this is my previous scheme, and you see that the scale that we would like to probe is really below 1 AU. And if we want to probe scales as small as 1.1 AU at 140 parsec, which is the typical distance of star-forming regions, we really need to have access to an angular resolution bigger than the milliarcsecond. And to do that, we propose to use gravity. So gravity is installed at the Perraut from ESO, and here you have the 4UT telescope that will be combined in the gravity instrument. So the light travels in tunnels and will feed the gravity instrument that is completely in cryostat to increase the stability and also to reduce the background because it works in K-band at 2.2 micron. And the first part is to check the quality of the beam and the pupil position through an acquisition camera working at 1.5 micron, and that allow to image at the entrance of the instrument the beam and the image. So you see the four, this corresponds to the four beam, the four telescopes, while the scientific photons in the K-band are injected in single mode fibers, again to clean up the beam and to increase the quality of the measurement. So here we are injected of these fibers that are pure fibers to increase again the throughput, and then through the fibers we can adjust the optical path between the different beams, and we can also control the polarization, for instance, here. And we have in parallel two different instruments. One is the fringe tracker, which is there to stabilize the fringes that we will record and to compensate for the effect of the atmosphere, while the second one is the scientific instrument that will record the astrophysical signal. So at that stage, we will combine the four beams in an integrated optic chip here. So each beam is splitted so that we can combine 2 by 2 the four telescopes. And then we disperse the light through a prism, and we have access to the fringe, 6 fringe patterns here as a function of the wavelengths. So why doing that is because when we combine interferometrically these four telescopes, is as if we have synthesized a giant mirror whose diameter equals the longest separation between the two telescopes, which is called the baseline. And here it's as if we have a giant mirror whose diameter equals 140 meters. It is as if, because the price to pay is we have no longer a beautiful image. We have a fringe pattern. This is this succession of bright and dark zones as a function of the wavelengths, since we have a spectrograph covering all the K-band with a spectral resolution up to 4,000. Doing that, we are able to probe the scale that we would like to probe, but we need to extract the information from this pattern. So I will not go too much into the detail about that, but just to give you a few information of what we can do. So from the fringe pattern, we can extract the visibility or the contrast of the fringes that give us access to the size and the geometry of the object we are observing. And we generally plot this visibility as a function of the distance between the telescope. And here it's a model of, for instance, a ring. So, and you see that here we measure the size, and here we have some difference according to the sharpness of the ring. You have the two models here, and you see that we can see some difference. What is important to record is that there is a Fourier transform relation between the visibility and the brightness distribution of the object. So provided you have an analytical expression of your visibility, you can do model fitting and have your measurement point here and compare with different models. We have also another quantity that is interesting is the closure phase that gives us access to the asymmetry of the object. So a symmetric object will provide a null closure phase, and for the asymmetric object we will have a departure from zero. And ideally, if you have a lot of visibility and closure phase measurement, since you have a Fourier transform relation between your measurement and the brightness distribution, you can reconstruct an image. And this is what is done in the millimetric range, because there is plenty of antennas, and then they can retrieve an image. But in the optical, because we have only a few numbers of telescopes, it's not so easy. And since we have a spectral resolution, we can measure the previous quantity as a function of the wavelength. So this is what you have here for the bracket gamma hydrogen emission line that we have in the K-band. And for each spectral channel, you can derive the size. So you can compare the size of your object in different spectral channels. It's a kind of tomography that you can do in the different spectral channel. And you can measure also the phase, that is the position of your fringes as a function of the wavelengths, and compare them, for instance, to the continuum. And this is directly related to the photocenter position of your emitting regions on the sky. So you can plot the position on the sky of your emitting region for the different colors or velocity. So this is what we used for our gravity large program. And so gravity has been installed in 2016, and we have led a large program dedicated to young stellar objects with the aim of taking benefit of the sensitivity and the accuracy of gravity to investigate the findings of the pioneering works on this domain within a statistical approach. And so this is on the bottom here, you have our sample. So we have about 50 young stars with mass ranging from 3 to 10. So this is the Herbig stars. And we have about 40 T-Tauri stars, that is more solar-like young star with mass of 1 to 2 solar masses. And for all these objects, we investigate both the dust distribution around the central star and also the spatial location of the line emitting regions of hot and warm gas, but mostly on the hydrogen gas, and to understand the excitation mechanism, the accretion, the ejection, and the kinematics of this gas distribution. So today I will focus mainly on the large program approach, and of course there is a lot of papers on really interesting individual objects, but I prefer to focus on the statistical approach, because I think it really the legacy and the added value of this lab program. I will start to what we have done with the study of the dust distribution at the inner edge of the protoplanetary disks. So with gravity, we extract sizes in the K-band, and we can plot all these measurements as a function of the stellar luminosity. This is what we call the radius-luminosity relation. And the green symbols correspond to the T-Tauri star, so the low mass star, and the blue correspond to the most massive star, the Herbigs. And you see that we have a trend with this kind of law that translates the fact that in the near infrared, the continuum emission is mostly tracing the sublimation of the dust at the inner ring of the disk. So due to the radiation of the central star, the dust is sublimate, and you have this relation that is coded or represented by this color line. What we can see is that, for instance, for the T-Tauri star, as we have several measurements, and also what is important is it's an homogeneous sample in terms of observing strategy, in terms of processing, and in terms of interpreting, we can look for trends with the central star properties and try to look for different families. And we see here a kind of plateau for the size that is interpreted as a stronger contribution of the scattered light for this low luminosity and cooler T-Tauri stars. And we see also that we have here a huge scatter for the large luminosity and probably some departure from this very simple passively radiated disk. In particular, we can have viscous heating of the disk due to this strong luminosity of the central star. We can have different properties of warming or cooling efficiency of the dust that we have, and we can have also some impact due to the gas, because the larger symbol correspond to object for which we have a bracket gamma emission, and we know that generally this emission is much more compact than the continuum one. That is to say that inside with our cavity, there is some gas that can shield the stellar irradiation. And now what we are doing is that we are using radiative transfer models for different luminosity. We can produce density map, temperature map that could be used to compare with gravity measurement. So we can define different dust population, different composition, for instance, adding some iron to olivine, or change the size of the dust with a very small grain here, to which we can add a larger grain. And this is a work that is led by Mathis Soulet, that probably some of you know very well, because he was here, he made his PhD here also. And this is the plot that he started to do. In gray, you have the gravity measurement, and we superimposed this the sizes we can derive from the different radiative transfer model. And for the different dust population, different dust mass of the disk. And so we can try to see whether we can explain, for instance, this scatter, or what is the most the model that is most consistent with our observation. So this is possible because we have a huge, a large sample that is also homogeneous. Something that we try to do also for the dust distribution is to have a look to the morphology, to the asymmetry of this dust distribution, and also to the variability of this part of the disk. So this is an example of an image reconstruction. So we have enough points that allow us through an inverse Fourier transform to reconstruct images of the disk around this T-Tauri star, these early stars. And we have several epochs in 2020, 2021, and 2024. And we see this arc that is brighter than the other because of the inclination of the object. And we see also some blobs orbiting the star. And to be convinced of the reality of these blobs, we also produce images across the bracket gamma line. And you see that when you do that, so the color code the spectral channel or the velocity, and you see that we have a kinematic maps around the central star corresponding to this white star, but also around this blob. This is the same epoch, and in these regions we clearly see also a kinematic map showing that we have probably here a blob with some gas around, so accreting at the time of these observations. And even if we are not able to reproduce images, we can also, when we have different epochs, because now we have 7 or 8 years of observations for some objects, we can do model fitting and look at the dust distribution for the different epochs. And this is what is plotted here. So the yellow correspond to the dust distribution, the best model that we have fit to our data. And you see that from one epoch to another, we have this crescent-like structure orbiting the central star that is represented by the white star here. And what is interesting also for these Herbig stars is that we are able to constrain the size and the position of the emitting regions of the bracket gamma lines, or the hot hydrogen. And you see that this is represented by this blue to red cycle. And the blue to red coded the velocity. And you see that the size of the bracket gamma emitting regions is quite small. It's 0.35 AU. So well within the inner rim of the disk that is more around 1 AU. And what is interesting is what you compare the different epochs. It seems that this gas emission is always between the star and this crescent-like structure of dust. So combining what we see in the dust and what we see in the gas help us also to better understand what happened, and to try to test what it could explain this crescent-like structure. Is it an increase of density? Is it an increase of scale height of the disk? And again, for this, we also developed a lattice transfer model to be compared to our observations. So, of course, having access to the measurement across the gas through spectral resolution allow us really to test the accretion and ejection processes at in the very central regions. And so this is the second part of my presentation. And again, you have the same scheme of the accretion ejection processes. So you have the sample star here. This is the disk I showed you previously. And here, this is where the dust is truncated due to the magnetic field. You see here the magnetic field line. And the material is accreted onto the star and produce some accretion shock. And all of this process, and of course we have also ejection through winds and jets, and all these processes have spectroscopic proxies. So if we combine spectroscopy with interferometry, we can probe this small scales here, thanks to the angular resolution of gravity. And with the spectroscopy, we have access to all the emission lines or all the change in the line profiles that is due to these processes. And if we use spectropolarimetry with Spirou in the near-infrared or Espadon in the visible at the CFHT, we have access also to the magnetic field strength or and topology. And we led a combined program with, in particular, with the colleagues in Toulouse, working on spectropolarimetry to combine the data set that we have to have a better understanding of these processes. So I will just show you a few examples. So it's a very small sample. So we have about 10 or 12 T-Tauri stars that has been studied, but we have already some findings. And to compare these T-Tauri stars, I have sorted them as increasing accretion rate, and we have reported the sizes that we measure with gravity in the continuum. So this is the red square. In yellow, you have the sizes we measure with gravity for the bracket gamma emitting region, and we compare that with the co-rotation radius, because if we are dominated only by magnetospheric accretion, we expect that the size of the bracket gamma emitting region will be very compact, very close to the star, while if we have additional processes, in particular winds, we expect to have larger sizes. And this is what we can do here. So at the bottom, it's the weak accretions, and you see that we have very compact bracket gamma emitting regions, about 5 stellar radii, which is typical the sizes that we expect for the magnetosphere. While for a stronger accretor, you see that the sizes can be much larger than 10 stellar radii. So probably on top of the accretion, we have also some ejection processes. So I will show you a few examples of weak and strong accretors. And just to give you an idea of what is our methodology, that we have developed 3D radiative transfer models to have some synthetic images of the accretion, to see the accretion funnels onto the star with the accretion shock here. This helps us to produce synthetic line profile, but also from the image, since we have a Fourier transform relation between the image and the interferometric observable, we can produce synthetic interferometric quantities that could be compared with gravity. So this is a development that has been done within the framework of the ERC SPD of Jérôme Bouvier in Grenoble. And on top of this model, we have had also a geometrical wind model, and to produce again quantities that could be compared to our measurement. So when we are in the case of weak accretor, for instance, for TW Hydra, this is the emission line that we record with gravity. From the gravity observation, we can derive the size of the emitting region as a function of the velocity. This is the blue to red symbols. And we derive a compact bracket gamma emitting region that could be compared with the size of the magnetosphere that we can extract from spectropolarimetry. And you see that it's well in agreement, confirming that the magnetospheric accretion scenario is dominant in that case. And from the radiative transfer modeling, we can superimpose. So in purple is the prediction by the model, and from blue to red here you have our measurement. So the agreement is really nice, and we are in I would say at an ideal case. Now, when we go to strong accretions, the scheme is a bit more complex. And here again, it's a synthetic prediction that we have with the different models. So in yellow is the previous model with only magnetospheric accretion. In blue, it's discrete only. And the hybrid model is the combination of the two. And you can see on the line profile and on the size of the emitting regions, the impact of the magnetosphere and of the wind. And the wind mostly contributed to the highest velocity, to the wings of the line here. And on the last column, you have the comparison between this wind model in purple with the black symbols that correspond to the gravity measurement. And you see that we are able to retrieve this U-shape variation of the size as a function of the velocity. We have do that also for another T-Tauri star, which is a twin T-Tauri star binary. And again, you see that we can trace the size as a function of the velocity. And we have two different symbols, square and cycle, because we have two consecutive nights, and we can compare the height is really to monitor what happened during the time. And you see that the size remains almost similar. And what I put here is what I presented to you previously is the photocenter shift of the bracket gamma emitting regions from blue to red here for the two consecutive nights. What is really striking is the scales that we are able to probe with the differential quantities, because you see that we see this photocenter shift that is almost a line, and with an angle with respect to the disk orientation in yellow. And you see that the scales that we are probing is really a few hundredths of AU. And this is really the scale that we would like to probe to investigate the formation of this closing planet. So this quantity is really useful for these studies. And this relation between what we measure, the differential phase, and what the quantity we derive, the physical quantity, is without a model assumption. And so from that, we can start to have a coherent view of the environment of this object, because you see that we are almost perpendicular to the disk orientation. So it seems that the process we are tracing is almost polar, but you see that from one line to another, we see no displacement or rotation of this trace. So we are not dominated by an accretion flow, because during from one line to another, it's supposed to rotate when the star rotates, because the period is about 3 days or something like that. So we have probably accretion, but we have also a wind contribution. And to go toward a coherent view of that, we can also use what we measure from the spectropolarimetry, and we can have a look to all these emission lines that could be tracers of accretion and ejections. And you see, for instance, the H alpha profile in the visible coming from our espadon measurement, and you see this deep absorption in the blue wings, and that is a tracer of strong accretion and also disk wind. So it's coherent. We can check the consistency between what we measure in interferometry and what we measure in spectroscopy. And of course, with the polarimetry, we can have access to the magnetic field signature is here in the circular polarization. You see this S shape, and that gives you access to the topology of the magnetic field. And combining those two is really powerful, because we can have some coherent view of this these innermost regions of our object, with the inner ring that is probed with gravity, so 20 stellar radii, the position or the size of the bracket gamma emitting region, the topology of the magnetic field, and we can put all the things together. So I will finish with a few perspectives, with the opportunities coming with Gravity Plus. So Gravity Plus is an update of the gravity instrument, but it's more than that, because it's also an update of the VLTI infrastructure. So the interferometric modes of the VLT at Perraut, and it's a phased project that has started in 2019, and with different phases and different how to say that phase that have tackled different limitation of what has been observed with gravity in terms of interferometric capabilities. I will not describe all these modes, and I will only focus on what is really important for the study of protoplanetary disks. But there is several phases that open also new avenues for different area and different topics. One of the first upgrade was on the adaptive optics of the UT, and that's why it's impacting all the instruments that are behind each telescope and not only gravity. And this gives us an improvement also of the. Yes, this is the image quality with the very old adaptive optics and with the new one. And the interest is that the light is much more focused, and then we inject more photons in gravity. So this is to simplify, this is the improvement. And the second improvement that is really a game changer for the study of protoplanetary disk is the installation of a laser guide star on each telescope, on each duty. So again, it's an improvement for gravity, but not only. And on top of that, it's also a kind of pathfinder for the ELT, because it's the same lasers and as though that will be used for the ELT. And why it is interesting for the YSOs is because with the improvement of sensitivity and with the laser guide star, we will be able to go toward less biased sample. Here you have a color diagram for different star forming regions of different ages, and in the gray dash rectangle is the target that are observable with gravity, and in the purple dotted one is the sample that is observable with gravity and the laser guide star. And you see that the laser guide star is the game changer, because it allows us to go toward more embedded and more fainter target in the red. And so it will help us to have really demographic studies and to remove bias, because for the moment our sample is only constituted of all the objects we can observe. So it's not a sample for which the parameters, we know that it is biased, and it will help also to test advanced models. And besides, it will allow us to have access to new classes of objects. So first, we will be able to go to lower mass stars. And I show you a few examples on T-Tauri stars, but they are more J and K spectral type. Why we know that most of the exoplanets detected so far are around M stars, so we really need to go toward low mass. So this is something that we have done very recently on the case of Kyoto. So it's a very complex environment with arc and spiral and with jet. So it's not a simple object, but I think there is no simple object. So and the mass is about 0.5 solar mass, and we are able to have a combined campaign of observations with Perraut in the near infrared. So we follow it during 40 days or something like that. That allows us to really have a look to the variability of the different lines, to determine the rotational period of the object, also to be able to see or to know where the accretion shocks are in front of us, and also to be able to know in which rotational phase we are when we observe with gravity. And we are able to retrieve also the magnetic field topology and to follow it during 4 years. And we see that the magnetic field is really unusual. With it is very inclined with respect to the rotational axis. We see also polarity reversal between the different epochs, and we see that the magnetosphere is really compact. And it's also interesting because it is what we see when we do the gravity measurement. We measure a bracket gamma emitting region that is very compact and as compact as the magnetosphere, and we confirm that the accretion is probably unstable, and which is expected because we have also photometric variability. And what is also interesting, and it's also something that we work on, is that with gravity we determine an inclination of the inner disk that is larger than the inclination of the outer disk measured with ALMA. And in spectropolarimetry, the measurement also favor an higher inclination for the star. So it seems that we have misalignment between the inner and the outer disk, and it seems that it's the outer disk that is misaligned with respect to the star and the inner disk. So this can also give some hints of what happened, what is the history also of this system. And it could be due to the fact that these objects are supposed to have a past encounter with a close-by system. So again, this gives us more coherent view of this object, and going towards a lower mass, it's also really important to probe the bulk of the T-Tauri star and not the brightest one. And the last point I would like to mention is that since we are able to go toward a radar object, we are able also to go to younger objects and to have access to the class 1 objects that are younger, more embedded, probably in a different regime of accretion. We thought that also the magnetic field are supposed to be stronger and more complex. So for the moment, we are convinced that it's more complex. Not sure that it's stronger because we have some. For instance, for the moment, the observations are not, and the detection of the magnetic field are not so easy. And with this kind of performance, we thought that we would be able to observe the iconic class 1 HL2 object. And so we try it. And so HL2 is iconic because it's the first beautiful image published by ALMA with all these rings and also gaps here that are supposed to be also probably shaped by planets. And so this is the size of the ALMA image, and this is the zoom that we make with Gravity Plus. So here you have the Earth's orbit, so you see that the best model that we have for the continuum emission, so the inner ring of the disk is quite smaller, but seems to have the same orientation. And we try also to zoom in, so to measure what we have in the gas, so in the bracket gamma emission line. And we know that it's much more compact, and it's so this is the only visibility I show you during this talk. But we see here some increase of the visibility in the line that is to give us some information of the more compact emission of the bracket gamma. And the idea is really also to test the accretion and on this younger object and try to see whether the magnetospheric accretion scenario I show you with this very simple scheme is also valid for this younger object or not. And this is an ongoing work, but it's really promising. So I will stop here. And I hope I have convinced you that you need to do interferometry. No, you are welcome to join what we are doing. No, it's really the combination also with different techniques and different wavelengths are really useful. And there is a lot of things to come with Gravity Plus. And for the class 1, but also for the monitoring of the accretion flow, because if we increase the sensitivity, we can try to trace the accretion flows at high cadence, lower than 1 hour. And also, there is also some development at CFHT to combine the Spirou and the Espadon together. So it's we now can project. So yes, we are pretty sure that we will have a lot of things to do in the coming years. Thank you, and I will be happy to take some questions.
Okay, thanks a lot, Karine, for the presentation. Do you have any questions for Karine? Yes.
So the modeling and the multi-technique, multi-wavelength observations that you've been showing are really interesting. Is there any prospect of being able to do that on companions that are surrounded by CPDs,
The answer is yes. There are some programs and some ideas to do that. There are some pilot projects that is led mostly by Guillaume Rodaro. Yet the idea is really to try to do that. It's difficult because of the because we will look for very tiny signals. But yes, there is there. I think he has started observation on that. So yes, this is a project, and if you are interested in, we can discuss also with Guillaume. I don't know, you know him or not?
Sorry?
Do you know Guillaume?
By name.
By name, okay. No, yes, I think it's a really it's a really interesting program, and probably we need also to push for modeling, and because having some prediction also help you to better define your observing strategy. After that, we need to be able to obtain times, because for this period, for P117, the pressure on the VLTI globally has been multiplied by 3, and on the UT, the pressure for VLTI observation with the 4UT is above 10. So it's a good news, because it was building gravity and pushing for gravity plus, but now the competition for the time is it's quite difficult. But yes, I think this kind of program is also in terms of yes, in terms of science, I think have to be pushed.
Yes. Actually, I have the same question, but for binary systems. Do you have any plan to also focus on binaries? I guess you wanted to have a homogeneous sample to begin with, so single stars. Do we have any prospects for binaries? It's more difficult, I guess.
It depends. If you would like to use interferometry to detect binary, it's really simple. I think it's the simplest science case, because I said that there is a Fourier transform relation between the brightness distribution and the visibility. So if you have a binary, you have 2 points, and you have two Diracs, and at the end you have a sign modulation in your visibility. For the Young binary, we had few, because we observe all the targets and sometimes say, this one is a binary. But we have also a few programs to try to study how the binarity influence the accretion process, because you can have a disk around each component, you can have a circumbinary disk, and you can have accretion flow between all of them. So we made a campaign on one binary system, and that is joined with also Spirou and Espadon observations, because it's also important to have the spectroscopic proxy to disentangle which emission is coming from the binary, from the secondary, etc. So there are some programs, but it's true that for the moment we have not really emphasized on that.
Yeah, so thank you, Karin, for beautiful talk, and very impressive, and convincing that the interferometry actually works and works for science. So maybe some people in here had some doubts about that, but I think it's gone by now. I was wondering more technical question. So the presentation of the instrument, this gravity instrument, was impressive, and it's beautiful realization. It works on combining 2x2 telescopes, which means that when you have n telescopes, there's a lot of processing to split the light and all this. So there's another way, which would be to combine all of them together, some kind of hypertelescope mode. Is that something that is coming for next generations, or is there something which an effect that hinders or makes the 2x2 combination more efficient than for the future?
So there is several developments because you talk about efficiency. So for the moment, with gravity, we have not this problem of efficiency because since we have a fringe tracker that allow really to freeze the fringes, we are able to integrate a lot on the scientific instrument. And so we have a fringe tracker that detects the fringes and that servo control the position at a frame rate of 1 kilohertz. And so this instrument should be fast and sensitive. But on the scientific instrument, where we disperse the photons, we can integrate for all these measurements is we integrate for 30 seconds, but for some project on faint star, we can integrate during 100 seconds or something like that. So the efficiency is either on the fringe tracking part, and there are some today there are some developments and some design that are pushed, in particular for the NIST colleague, to be more efficient, to push the sensitivity. I don't talk about that today because when I show you the color diagram here for our sample, you see that we are not really limited by the K-band sensitivity. We are more limited by the red sensitivity. And after that, the question is also, your question is also really valid if we would like to increase the number of telescopes. Because combining 2x2 4 telescopes request indeed to split, and we have this integrated optic chips that is for the moment it's 1 centimeter per 4 or 5 centimeters, so it's quite compact. But if you increase the number of telescopes to be able to do image reconstruction, you need more space to do that. So you can try to keep this approach and to combine your 4, 6, 8, 12 telescope all together in a chip, but at some point you will have a limitation, and you will need to think to a different approach. Yes, sure.
Thank you.
Yeah.
Thank you for this great talk. I'll keep some questions for the lunch. But maybe one question about Gravity Plus. Do you have it's amazing what's like the opening of the parameter space. Do you have now a sense of its limitations, or is there a limitation? And maybe one related question is like you show the AO loop here. Do you know if you are affected by a low wind effect, like things that we see in sphere, and does that affect the performance of the system?
So the limitation of Gravity Plus is not. There is two answers. On Gravity Plus by itself, I think it's too early to know. We are struggling to improve what we have when using the laser guide star, because in principle it's simple. Huh? You have your artificial star, and so it's supposed to open indeed a larger parameter space, but we need to learn how to operate it to tackle with different problem that is due to the way your artificial star is produced, etc., etc., the trace of the laser on the sky, and etc., etc. So we need to learn about that. We continue to work on something that I have not talked about, is the vibration of the UT. And so there is still ongoing works on this vibration aspect. And the limitation is more on the array itself. We have only 4 telescopes. So when you compare with ALMA and 64 antennas, we know for those who do radio astronomy, the images produced by the 6 antennas and 64 antennas are on the same object are completely different. So yes, the limitation is the number of telescopes and the baseline, because we have only 140 meter baseline, and the resolution is limited. And on top of that, the UT are not well positioned for the Taurus, for instance, because you see these 3 telescopes are almost aligned, so you are probing exactly the same direction, but we cannot move them. So there are a lot of programs to improve the infrastructure, and there are some white paper that has been submitted within the Expanding Horizons program of ESO, either to add another UT, and ideally to put it further away, to reach also kilometric baseline to really increase the angular resolution. And for the low wind effect, I don't know, but I will say yes. I don't know why we will be. Probably we will have this low wind effect to tackle for sure. Which is a bit a pity, because the turbulence at Paranal is quite fast, and so when it's slower, you hope that it will be more convenient, and sometimes you have this effect. But we see the low wind effect on the small telescope, so I'm pretty sure that we have also this effect. But the previous adaptive optic was so old that the improvement is quite high for the moment. But yes, we need to go more into the detail and try to see what we can improve.
Yes. Put our mind on dream bits. We have optic fibers that can travel thousands of kilometers in the ocean. Can you connect with the SIA telescope, so with any other sense in the future?
I think if we are able to connect with telescopes that are a kilometer away, I think we will take the VLTI.
Yes, that's a good answer.
No,
my question is to increase the baseline. You know, you can make it.
Yeah, there are some proposition. We can use Vista.
Okay.
That is closer. For the fibers, there were in the past a few pilot projects, particularly the Ohana project in Hawaii, led by Guy Perraut, and trying to connect the different telescopes at the summit. And they did that. So they have kilometers of fibers and trying to recombine the different telescopes. And I think the most difficult part was to be able to face the scheduling of the different telescopes. And Guy has to cope with this kind of difficulties, because if you have only 2 hours on Gemini and to we need time to debug these kind of things, and it was really difficult to have this scheduling part. But yes, there are some programs and some proposition in the Expanding Horizons telescope to have this kilometric baseline and using existing telescope.
So it's not a.
No, it's a dream, but
a
some people, yeah, it's a project because people are working on that. And, maybe Thomas, you can say more.
Yeah. We looked in free space possible propagation from the baseline because we were afraid of the vibration effect on the fibers. Sometimes we use it as sensors for seismic variations. So you have limitation of the vibration and also the variation drivers.
And there is also a project under Mo Wilson from the American colleagues on the Chara array, because they have 6 telescopes and they plan to have a 7th one, and the 7th one are supposed to be related by fibers. So you need to dig a bit to have your fiber in a quiet environment and in stable temperature also, because fibers is also a temperature sensor. And there are some pathfinder to run these kind of things. But we will not do that in the K-band with fluoride fibers. Because regarding the cost of the fluoride fibers, we will not be able to buy 1 kilometer of fluoride fiber for sure.
But thank you for the breakthrough. Just a naive question. All the information about the magnetic field come from Perraut or Espadon?
Yes.
And so you really need to have and so it's really not the same scale of what you are probing with the VLTI. So how do you need to make a model to understand exactly because Espadon will get a star, but you have no idea, no spatial information at all about where the connection of this magnetic field. You are at such a lower scale than what Espadon can give you. I don't understand how you connect the information you get from the polarization with Espadon Perraut with what you get from the bracket gamma informations.
There is 2 connections. The first one is to do this 3D radiative transfer model. You need to enter magnetic field topology, strength, etc. So we use the Spirou or the Espadon measurement to parameterize the magnetic field in these simulations. And then what we can directly compare is the size of the bracket gamma emitting region we measure with gravity, with the prediction. Indeed, when you have the strength of the magnetic field, you can predict. You need also the fundamental parameters of the star, you need the accretion rate, but you can predict where the magnetosphere are supposed to be. And so this is the connection that we have between our size and the measurement from the spectropolarimetry. And what is also interesting for us is really to know where in this simulation, for instance, when we do gravity observations, of course, the measurement will be quite different whether you have the accretion flow in front of you with the accretion shock here in front of you, or if it's behind. So the spectropolarimetric observations also give us a lot to face our observations.
You need simultaneous observation, or I can.
Yes, we need, but we need to schedule the observation at the same time, and it's really hard to change the scheduling for ISO. So generally, what we do is that we have the date of the gravity observations. And since the Spirou observations are done within the large program we are part of, we can schedule the Spirou observation. Generally, the Spirou observations here are for 2 weeks, but we try to sandwich our gravity observation. But for instance, for HFTO, yes, for HFTO, when we observe with gravity, we have 2 hours with gravity. We observe HFTO 2 weeks before, and we continue the observation. But when we have the gravity observation, there is no in a while. Too bad.
And moving to gravity plus, will it become a problem for Espadon for the target become too faint, or? So will you still be able to connect with all the?
With Spirou, yes. Yes, with Espadon, maybe for the faintest target, it will be more difficult. And we are not at the same place. So there is also, you need also an overlap. But we have I think we have, for instance, for the class 1, I think we have 20 or 25 common targets, so which is really interesting. It's a small sample, but almost nothing is known on these sources. So we will learn a lot. But yes, and now when you would like to go to large program, we need to face the thing, and the scheduling is really an issue. But more or less, we are lucky. So, but CFHT is quite. It's not so difficult when you have a large program and you can schedule your target. For the moment, it's fine. I don't know how it will go for the next call, but we will see.
Okay, so I think we can thank Karine again.